So I used to have these notes broken into 2 days, and I used to do a couple of these things in 2D and then talk about them in 3D. But the nice thing about vectors in 3 dimensions is that they work just like 2-dimensional vectors. So you don't really need an extra lesson for it. If we're thinking about if we're thinking in 3 dimensions, I kind of like to think about like the corner of a room. So you have like X, Y would kind of be like your piece of paper if I put it on the ground, and then Z is coming up. So you kind of think about the corner of a room, or think about putting, you know, a pencil through, like this would be like your normal graph paper, and then Z. In 3 dimensions, what's added is that Z kind of, but when our standard form I and J, instead of just I and J, you'll know you have a 3-dimensional vector if it looks like this. Oh, I gotta pick thin color. Like the vector 1, 2, 3 would be a 3-dimensional vector. Or you could write that as 1I plus 2J plus 3K. And if you have that K happening, that's how you know you have that 3rd dimension. You have a 3-dimensional vector instead of a 2-dimensional vector. I is the unit vector in the horizontal direction. J is the unit vector in the vertical direction. And K is the unit vector in that 3rd dimension. That's what lets us write it like that. Again, I, J, and K is just another way to write, like, just different than component form, but equal to it. I just don't know how your textbook's going to look in college. I know what it looks like if you take AP Calc here, but I don't want you to see that and be totally thrown on day 1 that vectors are Calc 3 and be like, well, at least you might not remember 100%, but you might be able to be like, all right, this is in there somewhere. So magnitude, nice thing about magnitude is it's still square root of the squares. You just got to square all 3. Still square root of the squares. So it's nice. All of these things are going to be consistent. When we find dot products, the process, when we learn dot products, we're going to learn it for 2-dimensional and 3-dimensional vectors all together because the process is the same. All right, convert -2, 1, 7 to standard form and find the magnitude. So standard form is I, J, K form. So we would write that as -2I plus 1J plus 7K. And then find the magnitude, do square root of the squares, and reduce it. And I'll meet up with you. I got 54 under the radical. Is that what you guys got as well? And 54 is 9 and 6. So 3 square root of 6, if you want to simplify that radical. So nice. At least, I know there are a lot of little things to remember with this unit, but at least they're kind of little consistent things. 3-dimensional vector, if we're going to find 4v plus 2w, which we've been doing since day 1, if v is -2i minus 4j plus 5k, and w is that mess right there, we can just distribute our 4, distribute our 2, and combine like terms. I like kind of working with the i's and j's because it is very algebra-y. Like, it feels very happy. So I'm going to find 4v and add it to 2w. Distribute, distribute, combine like terms. I'm going to treat this like a polynomial that I have to add, so okay. I like to cross things off as I go. In component form, that would be, we would write that as negative 16, negative 28. 30. You were asked for component form. Good so far? Okay. Everything today that we learn, you have an equation for on your equation sheet. Huzzah. Right? Good stuff. Okay. So dot product is one form of vector multiplication, and it results in a scalar number. So the dot product is used in many applications, such as finding force and torque. They've used it in physics. Question mark? Awesome. So to find the dot product of two vectors, you multiply the like components and add in the middle. So if we were doing dot product of u and v, we would do u1 times v1 plus u2 times v2. Again, the lovely thing is three-dimensional vectors work the same. You just have to add in the third dimensional component there. u1 times v1, u2 times v2, u3 times v3. Alright. Copying. Go ahead and flip and find some dot products, and I will catch up with you. The thing to be careful about if you have i's and j's is to look for a k. If you have a k in one, it's 0 in the other. So you can still find the dot product. You want to, like, if you had a I, J, and then a K, you would want to make sure that you kind of treat the other vector as a 0 in that Z direction. And you do get a scalar number for your final answer. So you're going to get a single number for your final answer, no variables. So 15 plus 8 is 23, and you don't have to show that middle step. You can use your calculator. Questions about dot product? It's relaxing, yeah. Let's flip over to the back of the notes. We'll do a quick application of dot product, and then we'll come back to angle between the vectors. So we'll come back to angle between. Let's go here. So this is parallel, and orthogonal vectors. Two vectors are said to be parallel if there's a non-zero scalar such that V equals some scalar times W. So your vectors are parallel if you see a multiplication relationship between them. If you take one vector and add 3 to both components, add 2 to both components, multiply, not add, online. So if you take one vector and you're doubling it, or multiplying by 3, or multiplying by 1/2 or 1/3, it's that multiplication relationship that is going to make them parallel vectors. Orthogonal, two vectors are orthogonal if the angle between them is pi over 2. Pi over 2 is 90. So orthogonal is just the vector word for perpendicular. Again, our goal in this unit is just a toe dip into how vectors are used in upper level mathematics. So I'm trying to get you all the operations that you'll need for later. One of the things is that orthogonal means perpendicular. Two vectors are orthogonal if and only if their dot product is 0. I can spell product. So if I'm looking at two vectors and asked to figure out whether they're parallel, perpendicular, or neither, the first thing I do is look for that relationship. Is there a multiplicative relationship between the two vectors? And then if I can't find one, then I look at the dot product. And if the dot product isn't 0, then I say neither. So it's kind of that's the process that I go. If you want to find the dot product first, you're more than welcome. That order doesn't matter. So, determine whether these are parallel, orthogonal, or neither. If it's easier for you to look at these in component form, which I like, it's helpful, I think, just to see the numbers, I would so as I'm looking at V and W for A, I have 1, 1 and negative 1, 1. I can't multiply my first vector and get the second vector. It would have to be negative and negative there. So since I don't see that multiplication relationship, I'm going to find the dot product then. To find the dot product, I'm going to multiply my horizontal components, multiply my vertical components, and add the middle. And when I do that, I get negative 1 plus 1, which is 0. Since the dot product is 0, the relationship between these vectors is that they are perpendicular, or the word that we use in vector world is orthogonal. All right, B. Again, I'm going to write out component form just because it's the easiest for me just to look at the numbers. Are they parallel? Do you see a parallel relationship happening? Yeah, I don't see one either. So let's find the dot product. Again, horizontals plus the verticals multiplied. And you can see already that it's not going to be 0. So 2 plus 4 is 6 is my dot product. So these are neither parallel or orthogonal. All right, vector V, I have 3, -4, and vector W, 9, -12. You see a multiplication relationship? What is it? W is V times what? Yeah, V times 3. And since I can take V and just multiply it by 3, get 9, get -12, these two are parallel. Right, we're going to do angle between vectors now. And then we're done. We can have some time for practice today. Get started. Backing it up. The angle between vectors is on your equation sheet. Yep. And the angle between two vectors is, it's always going to give, we're only going to do this with acute angle. So this, or I'm sorry, angles that are between 0 and 1. But not just angles between 0 and 1. So I've seen a proof for this. You can, I think there might be one in the textbook. But the way you find the angle between two vectors is to do cosine of theta. We're solving for theta. Is the dot product of our two vectors divided by their magnitudes multiplied. Practically, the way you'll use it and the way you'll put it in your calculator is this. Theta equals arc cosine of the dot product over the vector, over the magnitude. This unit in particular, there are a lot of the little, like the little bitty equations that you have to, and I know you guys don't have to memorize this one, but the words help me more than the equation itself. Whereas like in Algebra 2, when I had to memorize equations, I kind of like, you know, whatever, saying the quadratic formula. No, that's how you guys do it, right? Or whatever, however Mr. Graham's saying it to you. But for me, all of these, I think are kind of easier to think about in these little, like, dot product over the magnitude, or, you know, subtract the, like, components, or subtract the, like, variables. Okay, I think we'll only need 2 practice problems for this. I don't think we need the big monster triangle problem. I think our time would be better spent practicing some other things. Let's do these 2 nice and thoroughly. So, find the angle between the 2 vectors, u and v. I'm just going to do theta equals arc cosine dot product. So I'm going to do 2 times -2 plus 3 times 5. All divided by the magnitude. So the magnitude of my first little guy over there, 2 squared plus 3 squared, square root of it. Magnitude of my second, negative 2 squared plus 5 squared. This used to be a monster to put in the calculator before the new operating system, before the TI Inspire, where you could do the stacked fraction. If you can't do the stacked fraction in your calculator, let me update your calculator for you. The other thing you need is you need to be in degree mode for this. Vector problems are the only time. I don't know why I made that a smiley face, because degree makes me sad. But you want to be in degree mode. We do vectors in degrees. That's it. Maybe smiley face because it's Friday? You should get 55.491, and I do strongly suggest that you practice putting that in your calculator. And make sure that you know how to do that stacked fraction. In the TI-84, it's alpha, y equals enter. I was working during study hall yesterday, I was working with a geometry student on probability, and he was doing all these fractions in the calculator without the new operating system. And I updated the calculator for him. He's like, I don't know. It's just such a mathematical life upgrade to have that option. Yeah. Yep. Yeah, so three-dimensional vectors, this equation works exactly the same, which is really nice. So you still are going to find the dot product. You're still going to do the magnitudes. You just do the 3 together instead of just 2. So I see people punching in their calculator, so I'm just going to pause while you practice. Make sure you can get your calculator into degrees. I know that's kind of more of a thing for the Inspire than it is for the 84. And then I would, on after Wednesday, just make sure you flip back. All right, let's work this three-dimensional vector. And then I'll come around and help you with your calculators if you need it. So we're going to do arc cosine of the dot product. So here's 3 times 1 plus 1 times 2 plus 3 times 2 all over the magnitudes. And here you just have your 2 magnitudes, but your 2 magnitudes are each going to have the 3 components. 3 squared, 1 squared, and 3 squared, all under the square root. 1 squared, 2 squared, 2 squared, all under the square root. And you're going to want to put it in your calculator just like that. You should get 32.734. Practice with your calculator and make sure you let me know if you have questions about how to put that in. I would show it to you, but my calculator is still freaking out up here on some polar coordinate thing from like 3 weeks ago. So Alright, I'm going to give you guys the rest of the class period to practice. There's practice. The next page of the packet is practice. There's Math Excel.